Comparative analysis of initial cost between conventional and energy-efficient building using BIM as a tool, a case study approach. Abstract energy-efficient buildings have gained a lot of significance in recent years due to more emphasis on energy conservation. There is a general perception amongst the stakeholders that energy-efficient buildings will always have more initial cost as compared to the traditional conventional buildings. The present research compares the initial cost of major elements such as building envelope, mechanical and electrical systems for conventional and energy-efficient building. The effective use of building information modeling, BIM, to understand the cost management aspects is also discussed. The findings of this study indicate that the initial cost of energy-efficient building can be significantly lower compared to the conventional building. The study also highlights the effective use of BIM to estimate the major cost drivers associated within the building. The flowchart for comparative initial cost analysis between conventional and energy-efficient building can provide significant insights to the different stakeholders in promoting energy-efficient buildings. Keywords: buildings, cost management, building services, building information modeling. 1. Introduction. Energy conservation in buildings has received a lot of significance in recent years. There is a growing demand to construct energy-efficient or energy-compliant buildings globally. In India, Energy Conservation Building Code, ECBC, has been framed to address the energy performance standards for new commercial buildings in India. A study on the critical aspects of energy efficiency and management in buildings was conducted by Danish ETAL, 2019. Adopting different energy-efficient strategies can have significant impact in reducing the energy consumption of a building, Sadanani ETAL, 2011. Pacheco ETAL, 2012, have reviewed different building designs that can reduce the energy demand of residential buildings. Dhaka ETAL, 2014, investigated the effect of building envelope on the comfort conditions for a naturally ventilated building. An integrated design approach was recommended by Jones and Bogus, 2010, for achieving energy-efficient retrofits in a building. Jadhav, 2019, investigated the strategies for reducing cooling load for buildings and improve the energy efficiency of building. Kilian and Kozek, 2016, have discussed the use of model predictive control for energy-efficient buildings. Hong et al., 2020, have addressed some of the important questions related to urban building energy modeling. Building information modeling, BIM, can be looked upon as an important tool in project management, Bride et al., 2013. Smith, P., 2014, examined the global issues related to project cost management and investigated the role of BIM in cost estimation in the construction sector. Gu and London, 2010, evaluated the readiness of architecture, engineering, and construction, AEC, industry for adoption of BIM technology. Abanda and Byers, 2016, investigated the use of BIM to predict the impact of energy consumption due to the orientation of the building. Sadagifam et al., 2019, studied the effect of building components for a residential building located in tropical climatic zone. Gergs et al., 2019, investigated the role of BIM at the conceptual design phase by analyzing the case of a UK construction project. There are studies on use of BIM for various applications reported by few researchers around the world. Basarik Gerber et al., 2012, Chen and Tang, 2019, Digi et al., 2015, Jenkins, 2018, Kaziltas and Akinci 2010, Ozturk, 2020, Stumpf et al., 2009, Jadhav, 2019. ICAB, 2015, have documented the experiences and case studies from architects, consultants, and building owners on several energy efficiency aspects in a building. The preceding literature has limited information on the initial cost aspects and its variation between a conventional and energy-efficient building. This information is important to understand the cost implications for promoting energy-compliant building. 2. Research objectives. The purpose of this study is to understand the important cost engineering parameters for analyzing the initial cost of a building. The specific questions that needs to be investigated in the present study includes: 1. What is the variation in the initial cost of a conventional and energy-efficient building? 2. Can BIM be used as an effective tool to estimate the initial cost of a building and perform comparative analysis? 3. Research methodology. This study uses a hypothetical building case study constructed using a BIM interface. A simple commercial layout is evaluated using variations in the building envelope and subsequent variations in the construction cost of civil, mechanical, and electrical components. The commercial office building layout is shown in Fig 1. H:/T/research plan _2019, 20/BIM/imp_ for higher end research paper _BIM references for papers /research paper _ECBC and BIM /data/1.jpg. Fig 1 Layout of office building. The commercial office building in the present study has 3 floors with total floor area of 7,320 square m, with each floor of approximately 2,440 square m. The building location is assumed to be in Mumbai, India, which falls under warm and humid climatic zone. The building envelope is analyzed for both conventional and energy-efficient construction type, to understand the variation in the mechanical and electrical requirements of the building in relation to the building envelope. The building model is analyzed using Autodesk Revit, BIM, software. 3.1 Comparison between conventional and energy-efficient building. One of the major differences in the conventional and the energy-efficient, or compliant, building lies in its building envelope. The ECBC, 2017, has prescribed few guidelines in terms of building envelope depending upon the climatic zone. The building model in the present study is analyzed by comparing the building envelope for conventional and energy-efficient building, refer Table 1. The selection of building envelope for conventional building is referred from the general practices adopted in the construction sector, whereas the selection of building envelope for energy-efficient building is referred using ECBC, 2017, guidelines. Table 1 Building envelope. Category: Conventional. Energy. The building construction materials are selected in Revit software based on the options available in the software. One can select a building material from the software default options that matches with U value and SHGC of actual building material to be used in the project. It is also implicit that subsequent iterations are possible by modifying the building construction material and its geometry. 3.2 Variation in the cooling load requirements. The building envelope plays a significant role in the cooling demand of a particular building. In conditions where the outside temperatures are high, it is recommended to use building materials with lower U value to provide less heat gain inside the building. This results in drastic reduction in the cooling load requirements. The building model, refer Fig 2, is simulated using Autodesk Revit, BIM, software to understand the variation in the cooling load requirements of conventional and energy-efficient building. This reduction of 77% in the cooling load is possible due to the selection of building envelope with lower U value, for energy-efficient building, in comparison with the conventional building. 3.3 Variation in the initial cost for civil, mechanical, and electrical components. The purpose of this section is to understand the impact of energy compliance on the major cost drivers of a building. The cost engineering parameters that indicate major difference in the initial cost of conventional and energy-efficient building are building insulation, civil component, air conditioning system, mechanical component, and building electrical distribution, electrical component. Following are the assumptions considered for calculating the initial cost of civil, electrical, and mechanical components. 3.3.1 Assumptions. 1. The energy-efficient building envelope has insulation of 75 mm polyurethane for roof and 50 mm expanded polystyrene insulation for wall. 2. The air conditioning system considered is unitary air conditioning. 3. Cost of unitary air conditioning equals 35,000 INR per TR. 4. Power consumption for air conditioning equals 1 kW/TR. 5. No of computers equals 50, computer load, 65 W per computer. With the above consideration, the connected electrical load for conventional building works out to be 529 kilowatts and for energy efficient building as 169 kilowatts. Thus there is significant reduction of 68% in the connected load. The major cost of electrical system includes cost of components such as transformer, cables, distribution panel and load break switch. The rate analysis for civil, electrical, and mechanical components is considered based on data available in open literature, standards and equipment catalogs. Table 4 highlights the variation in the initial cost between conventional and energy-efficient building. It must be noted that the only variation considered in the civil component is the building insulation cost. 4 discussions. The following section discusses the findings to the key questions raised in this study. 4.1 What is the variation in the initial cost of a conventional and energy-efficient building? Several case studies in the past have shown the potential of energy-efficient buildings. Various simulation tools can help the designer in arriving at a comprehensive understanding about the impact of various building components on the energy consumption. Abeza, 2008. Sastry, 2016, highlighted the deep green retrofits implemented at Infosys. Taleb, 2014, analyzed the benefits of different passive cooling strategies on the energy performance of a building. The Energy Performance Index, AP, was seen to be reduced by 32% in Aranya Bhawan, Jaipur, Eesha et al., 2015. This was possible due to implementation of efficient building envelope and air conditioning system. Indira Paryavaran Bhawan, Prashad and Eesha, 2015, can be seen as a new paradigm of self-sufficiency. The above literature demonstrates the benefits of energy-efficient buildings. Energy-efficient, or compliant, building requires an energy-efficient building envelope. The need of insulation thus becomes significant as there is necessity to reduce the U-value of building envelope, refer Fig. 4. However, the fundamental question on the variation in the initial cost between conventional and energy-efficient building is investigated in the present study. The cost of civil component in energy-efficient building is more than the conventional building due to extra cost of insulation. However, the efficient building envelope reduces the air conditioning demand drastically, which further reduces the sizing of electrical components. In the present study, the air conditioning cooling load got reduced from 445 TR to 103 TR. This resulted in saving of approximately 1 crore 19 lakhs INR in the initial cost of mechanical, air conditioning, system, approximately 77% reduction. Further, the electrical demand got reduced due to lower capacity of air conditioning system. The reduction in the initial cost of electrical system was approximately 24 lakhs 87,000 INR, approximately 67% reduction. The results of Table 4 indicate that there is a saving of 18% in the initial cost of energy-efficient building in comparison to the conventional building. It is a general perception that energy-efficient buildings are costlier to construct than the conventional one. However, the present study highlights the need of a comprehensive and integrated approach to understand the benefits of increase in building insulation cost and subsequent reduction in the initial cost of mechanical and electrical systems. The practice of integrated approach, Jadhav et al., 2014, can bring considerable change in the sustainable development practices in building projects. The above comparative analysis of variation in the initial cost of major building parameters can increase the confidence of stakeholders and help in promoting the concept of energy-efficient buildings. 4.2 Can BIM be used as an effective tool to estimate the initial cost of a building and perform comparative analysis? Estimating cost of building projects is often a complex and challenging task. Use of software helps to ease out the process, especially when the quantum of work is exhaustive and the number of iterations is quite large. Energy and thermal simulations can help in achieving improvements in building design, Examaja, 2015, and sustainability goals, BISVAS, ETAL, 2013. BIM can be looked in the dimension of both technology as well as process, IJERT ETAL, 2012. Turk, 2016, has addressed some of the important questions related to BIM. BIM and energy simulation has gained increasing attention in the building sector, Lewis ETAL, 2019. Value engineering and cost estimation must begin at the early stage of design process to ensure cost-effective project delivery, Forges ETAL, 2012. Folk ETAL, 2014, have reviewed over 180 recent publications on use of BIM for existing buildings. The results revealed limited use of BIM in existing buildings. Early decisions on cost aspects related to building envelopes can improve the cost certainty of building construction projects, Idowu and Lam 2019. Eastman ETAL, 2011, have also summarized the lessons learned, in the form of case studies, by different stakeholders using BIM across all phases of the project. Gergs ETAL, 2019, in their investigation analyzed the benefits and limitations of BIM for a construction project. The authors found visualization and coordination to be the two main advantages of BIM. The effective use of BIM in studying the initial cost variations for major building components is discussed in the present study. The present study demonstrates how BIM can be integrated in analyzing the cost of energy-efficient building. The iterations in the building envelope can be applied to the model developed in BIM. The air conditioning load calculations can then be simulated to calculate the variation in the equipment sizing. Thereafter, the electrical equipment sizing can be determined. Thus, the number of iterations in the building envelope, civil component, and subsequent variation in the mechanical and electrical components can be demonstrated with better accuracy and speed compared to conventional design process using BIM. The use of BIM can supplement the cost estimation process effectively. The results obtained through BIM can be integrated with Excel software to perform the cost calculations and subsequent comparisons. The overall methodology of comparing the initial cost between conventional and energy-efficient building using BIM is indicated in Fig. 5. The application of BIM, Battle ETAL, 2017, can be extended from 3D to 10D, comprising of different dimensions such as design, schedule, cost, sustainability, facility management, health and safety, lean construction, etc. The cost estimation process, 5D, can be reviewed and aligned with scheduling, 4D, as well as energy and sustainability, 6D, using BIM. The benefit of BIM can be seen in presenting the data to different stakeholders in a simplified form. 5. Conclusions, limitations, and further research. It has been observed that lack of good research in terms of case studies is one of the major reasons why energy-efficient buildings are not getting promoted. A general perception that energy-efficient buildings are costly to construct has been challenged in the present research. In fact, the present study reveals that energy-efficient building are less costly compared to conventional building, if an integrated approach is taken into consideration. The comparative analysis of initial cost engineering parameters for conventional and energy-efficient building are investigated using BIM as a tool. The use of BIM as a tool is nowadays becoming increasingly popular amongst architects and engineers, as it allows the team to work on a centralized model and each one gets the access to the latest file version while working on a particular project. The present study provides insights into the initial cost dimension of a building by considering major parameters such as building insulation cost, air conditioning cost, and cost of electrical distribution. This study has few limitations which can be considered in further research. This study has considered only one building layout and only one climatic condition. The variations in factors such building layouts, building envelope optimization, alternative air conditioning systems and their impact on the initial cost is not addressed in this study. Though the trend of the result remains the same as seen in Table 4, yet it will be an interesting research to see the percentage variations in the initial cost. The authors have made an attempt to enable the readers understand the role of integrated approach while working on the cost management of building and building services. A further research in this connection will be to integrate initial cost of additional features such as renewable energy, wastewater treatment, efficient lighting, advanced sensors, etc. in an energy-efficient building and studying its operational benefits. The present study highlights only the variation in the initial cost between conventional and energy-efficient building. It will also be interesting to see the cost variations in the overall life cycle cost between energy-efficient and conventional building through some real-life case studies.